Hey, what's up? Welcome to this series of DC-DC power converters. We will see buck converter CCM mode today. In the previous video, we got familiar to the DC-DC converters. If you didn't see that, then you may find a link in the description. Let's get started. As we know that buck converter gives the output with lower voltage level as compared to the input. If we have 12 volt on the input side, then we will get the output less than 12 volt as shown. Here in this picture we can see that we have the input of 12 voltages and the output of 5 volt. Now moving towards the circuit diagram of the buck converter, this diagram is the simplest version. For more understanding, let me simplify it bit more. That removing the energy storage elements and the diode, we see that as the switch is closed, the load is connected to the source, and when the switch is open, the load is connected to nothing. The output voltage pattern will be like rectangular wave, or you may say that a PWM wave, pulse width modulated wave. Now I am going to add a capacitor. Oh wow, we found a little bit change in the wave. Capacitor is charging while the on time and discharging while the off time. Now the output is available for the more time as compared to the previous one. And the wave would be something like that. Now I am going to add the inductor and diode. As inductor has the property that it will not let the current to go to zero. So at on time it will charge, and at off time it will discharge. So the wave do. This is much for understanding. Now moves towards some mathematics and the design of it. In this video, as we are only talking about CCM, then inductor current will not go to zero. To start the calculations, we need to know the voltage second balance. This is a law in front of you on the screen which tells us that the voltages across the inductor for the on period times the on period, and the voltages across the inductor for the off time multiplied by the off time period divided by the total time is equals to 0 as shown. Let's say we have a total time Ts and a factor D varies between 0 and 1 named as duty cycle. With the help of our friend D, we find dts as an our on time, and we find 1 minus dts is our off time. Now we need to find the VL or an inductor voltages for the on time and the off time. As you see that VL on is equals to Vn minus V out, because the switch is connected for this time, so that VL on into T on is equals to V in minus V out times dts, and similarly for the VL off multiplied by T off is equals to minus V out into 1 minus dts. Here the negative sign presents the change in polarity of the inductor. As we know, when we will turn off the switch, the diode will start conducting, and the inductor will start feeding to the load, so the polarity of the inductor will be reversed for this time. Let us put these values VL on into T on and VL off into T off to the equation 1 to get some results, and now we will solve for the relation of V out over V in. This V out over V in is also known as MVDC. You may say V out over V in is equals to MVDC. For an ideal converter, the input power is equals to output power, so the relation of this MVDC or V out over V in could be converted into the I out over I in or I in over I out. We can see these relations with the help of waveform also. As we know, the voltages of inductor is given by VL is equals to L di over dt, so just convert it into current, put the value of the voltages, and we see that delta I positive is equals to V in minus V out into dts. All same steps to get delta IL negative, and here we go. By comparing these relation delta IL positive and negative, we get V out over V in is equals to D. If you have any confusion or any question, then you may comment. I will respond ASAP. If you like this video, then hit the like button and push subscribe also for more video. Bell icon is important, so click it also. Thank you for watching this video. Stay blessed.